Okay. Welcome to today's lecture. Very good morning. Before I start my lecture on the new topic, let me want to give one point on the previous lecture. There was a typographical error on the characteristics of output power in megawatt versus water discharge meter cube per second, where the head H3 is less than H2 and less than H1, and that's very important. So if you look at the characteristics, as the output power increases, we are looking at a water discharge in meter cube per second. For example, in case of H1, for a particular value, say around here, you need to have a bigger head, whereas for H3 is very small, but you get the same power. As the power increases, you can have a look, for example, this condition where the head is very less for water discharge is very less for H3, whereas the water discharge required for H1 is very high. So H3 is less than H2, less than H1. So it all depends on the head size of your hydropower plant with respect to the output power generated in megawatt. Today, we are going to continue our lecture on the next topic, which is we have seen economical load dispatch, how the modern trend is working, and how the traditional economic load dispatch optimization algorithms we have seen, because it's very important for a hydropower plant. When comparing to other power plants, the combination of hydropower plant and thermal power plant starts with the conventional um, economic load flow analysis. So today we are going to discuss a big broad topics, very important. One is the frequency control, which is called F control, load F control. Q is the reactive power control, and V control. Today we are going to discuss something on frequency control, the conventional techniques, and V control, not the Q control, because we can't be able to finish it because it's a broader topic. The next lecture, we will be discussing the discretized form of F control and Q control together. This was a plan. So the objective of this complete topic is to provide you the characteristics of generators, which particularly synchronous generators, and how the load frequency control is done in traditional aspects. Of course, now still modern power electronics application comes. Still, all the power plant does not 100% become digitalized. So still we are using the conventional load frequency control for controlling the power plants. In this case, we will have a look how these mathematical models are done for the power system, particularly on a single, double, three area power system with and without integral control. So it's a integral control means how to integrate all these power systems in single, double, and three areas of power systems. Then we are interested in looking at steady state dynamic analysis. So steady state is very important. Dynamic analysis able to understand the behavior of the systems during various perturbation or disturbance or transient conditions and the dynamics of the power plant. Then we will discuss in the next lecture why we need reactive power compensation. As your power engineers with the backgrounds, you already know what is the meaning of reactive power. So we are going to look inside why we need to compensate these reactive power in the perspective of power systems. Then the objective of load compensations, which includes two types of compensation we are going to look. One is compensated, uncompensated transmission lines. Then we are going to discuss on the concept of subsynchronous resonance, voltage stability analysis, and voltage control. Finally, we will look the methods of voltage control, calculation of rating for synchronous phase modifier. So these are the goals of this lecture, what we are planned to have. But as I said, I have divided it into two parts. First part, we are going to discuss on load frequency control, conventional methodologies, along with voltage control. Finally, the next lecture, we will discuss more on advanced frequency controls and reactive power compensations. As always, it's required why we need these control. That's most important because in any power system, we don't want reactive power. and we want to keep the active power maximum, and the active power, which is the power delivered to the consumers, we always need to be steady and of course constant. So that is the aim of designing all these control algorithms, particularly with respect to the frequency. The standard scale allowed is plus or minus 2% variation. For example, in real time, you can go and see in our grids or accessible single phase power supply where you can't find exactly the 50 hertz. It can be 49.12, or even sometimes in worst condition, it goes to 48 hertz for a weak grids. So in this case, we are trying to keep 49.25 like that near to the 50 hertz. So the allowed margin for permissible changes is plus or minus 2 percentage. So how to do that? We need controllers. What is a control? A control is a combination of gain parameters, integral parameters combined together, which can be able to operate the system for the desired performances when there are small changes happen in the load, which can make the frequency and voltages variations. So we have to design a control, frequency control, which take as all the deviation, either even if it's from the generator or from the load side or because of the transmission lines. If there is a variation in the voltage and frequency, the controller will adjust its value and make to operate the system in the desired parameters with a variation of plus or minus 2. If you design for plus or minus 1, it's up to the power system engineers who design the controllers. So as you know, when there is a change in the load become very large, if there is a drastic change in the load, very large margin change of the load, then the controllers cannot work uh, either manually or automatically. So we need to change the design of the controller for its gain margin, and of course for the frequency margin in terms of frequency analysis, or in general I want to adjust the value of the gain constant, integral constant, which I adjust manually for operating each margin of control. So in general, any control systems which is designed can't operate from 100% to 0% of variations. It can tolerate like 20%, 30%. I can give you a simple example. When your speed is controlled at 1500 RPM is a rated value until, for example, 950 RPM or 950 RPM, your regulator, I mean, the controller can work very effectively, whatever the variation. But when you're trying to change the speed from 50 percentage, say 1500 to 750%, we can't guarantee your controller will work very efficiently. So it's a different margin of operation, perturbation conditions. So every time the system needed to update its gain value for the gain parameter and for the integral parameter. If the controller is designed with the derivative, then the derivative gain. So we have three types of gain: gain for the gain for the integrator, gain for the derivative. So the gain needed to be upgraded or adjusted based on the operating mode of conditions. Why we need a frequency constant in our power system? That's very important. So you already know that is the best example. All our power generators are the obviously a motor. If you operate as a generator, it's in opposite direction. So the machine is the same. Is a synchronous machine or asynchronous machine. The machine is the same, but you operate the machine as a motor or a generator. For example, in case of a motor, we need to keep the speed constant. What is required? The frequency needed to be kept constant because your speed of your motor is decided by 120 F by P. So P is a fixed poles of the motor. We don't change. But think about the frequency. If you want a constant output speed, you have to fix your frequency to a constant value. So that's why, in a simple example, why we want a frequency constant. For example, in process industries, it's very important. Chemical process industries, very dangerous. Nuclear process industries, very dangerous. We need to keep all the parameters within tied value. So we need to keep the frequency always fixed. Of course, in case of a large power system, what we are working and our focus, we need to keep everything is in synchronized way operation. So the power frequency needed to be a constant. For example, if the frequency get affected because of the power transmitted to the interconnecting lines, then obviously the power available at the load center or the consumer end will be hugely affected. Because we already seen in our previous discussions, maybe also in the last semester when I was teaching you with respect to power quality, if there is a small change in the frequency, which is not 50 hertz, and all our systems on the load side, which is having a start point. So generation, you have a star generator, transmission is delta, distribution side where the consumer is available, we have star connections. So this case, it's very important that frequency should not be changed. If there is a change, then you generate the frequencies which are uh, not 50 hertz. It can happen also for your other frequency level at lower order harmonics or higher order harmonics. Then you produce a lot of heat in the systems. Then your system's reliability and lifetime may change largely. So during my presentation, if some of the candidate want to join, I request you please admit because I'm concentration on my presentation. Meantime, if some of the candidate want to join, let them join, and one of you could allow them to admit. Thank you for your help. With this, I can say finally, example, electrical clock. If the frequency of the electrical clock doesn't have a constant frequency, then the motor which is available in your clock cannot be synchronized. You can't get a smooth variation of your time in periodic way. This is a simple example why we are looking for the frequency control. Then how to control the frequency? That's very important, load frequency. We start with the basics. So we already know what is the kinetic energy. The kinetic energy is given by 1 by 2 times of your current into frequency square. So you can see the kinetic energy is directly proportional to the square of your frequency where omega equal to 2 pi f, 2 times your frequency. So I can say the kinetic energy is directly proportional to the square of your frequency and directly proportional to your current, which is a moment of inertia for the rotating parts. So this gives you a clear idea why the frequency plays a critical role. If a small drop in frequency, what happened to your kinetic energy? It reduces by 2 times because it's a square. So frequency square, a small drop in your frequency can affect your kinetic energy largely. So for example, to understand the system better, we keep a term called delta F, which is a change in frequency. Usually these change in frequency are sensed by your sensors, which are available in the grid system or power systems. By using voltage sensors and current sensors, we get all the feedback of your voltage and current. Then we calculate what is the frequency. Based on the variation in the frequency, the controller can able to generate a new signal which can able to control the frequency variation of delta F very near to F. That is a goal by which we can able to control, of course, the both the real power on the input side as well as on the output side. So please note your kinetic energy is directly proportional to the square of your frequency. A small change in frequency can affect greatly your kinetic energy. Then we go little inside the system. So for that, we are taking a characteristics. A typical characteristic of a governor of a steam turbine as shown here in per unit value, where you are.
Sorry, excuse me. Please, are you showing something on the screen? Because the slide is just on the front page. Is there something you're showing?
Yes, I'm showing here. Yes,
Yeah, it seems we're not seeing it because it's just on the front page.
for you. But I am moving here. I don't know what is the problem. Uh, could you see my screen now?
Yes, now we see. I see it at least. I don't know the others. Can you see?
Please confirm, please. I don't know what is you are looking at another end. You have to inform me. Otherwise, it's very difficult. Could you able to see the screen?
Yeah, I can see now
Okay, that's
objectives.
great.
Yeah.
Fantastic. So, do you want me to repeat again or I continue? Okay. So we have seen why we are looking at. I just give you an outline again back because we are going to look at today the characteristics of the generator, which is particularly synchronous generators, and why we want load frequency control is our main discussions. Then we are going to look at on mathematical models for single, double, three area power systems. Particularly with and without integral control, that's very important. We are going to look on a steady state dynamic analysis and the reactive power compensation, why we required in the power systems, objective of load compensation, which is very important. In two ways we are going to look. One is on compensated, uncompensated transmission lines. The concepts of subsynchronous resonance, we call it as WSR, voltage stability, and voltage control overview. Of course, we are going to look at what are the methods of voltage control and calculation of a synchronous phase modifier. As I said, the why we are very important the frequency control. Could you please confirm all the slide is visible to everyone when I change?
Yes. Yeah.
That's great.
Introduction
Okay.
now.
Oh, fine. So why we look at frequency control is very important. We always want active power to be controlled and reactive power needed to be controlled, and we want reactive power to be minimized as much as possible. So we want a steady power in our power systems, which is active power delivered from the generator to the transmission line towards the consumers through distribution networks. The allowed maximum limitations for the frequency deviation. For example, we have 50 hertz systems, but obviously we will not get 50 hertz. 49.1, 49.2, even some worst cases, 48 we get. But as per the standards is allowed 2%. So 2%, you know the meaning out of 50. So maximum it's 49.5, 49.2 is always the stable frequency we get from the generators. Then particularly how we are controlling all these frequency by using controllers which are designed for frequency control. When the load is changing drastically or minimum values, you have the controller of the frequency controller will have a gain controller, an integral controller. Sometimes it has a derivative controller combined three together, and the gains of these three parameters will be adjusted according to the different operating conditions, because the fixed values can operate between say 100% to 80% or 75 percentage variations. I say 75 percentage margin towards 100% of the rated value of the frequency, not below 75 percentage. So we need to adjust the gains of your gain parameter, frequency parameter, sorry, derivative parameter and integral parameter, so that PID is continuously tuned for a different operating conditions. So one sets of value can't be work automatically or manually with a large deviation of the frequency. So it should be controlled on regulating the values of the gain. Why? What is a necessity? Is an example I showed you. In AC motor, we need to keep the speed constant. If you want to keep the speed constant, you need to keep the frequency constant, because the speed of the machine is 120 F by P. Either is a generator or a motor is the same 120 F by P. So the speed, the synchronous speed is directly proportional to your frequency. Best example is a process industries, nuclear power plants, where sensitive process are done with all these synchronous and asynchronous machines, where the speed needed to be constant or process needed to be constant in process industries. So the frequency play a vital role in maintaining a constant value. In power systems, yes, we want the complete power system to be synchronized with the synchronous speed of operation, and the frequency needed to be delivered to the consumer in a fixed value near to the 50 hertz is our goal. So we need a strong constant frequency control for large power system networks. It has to be noted the frequency can affect it because of the power transmitted between interconnecting lines. When the bus bar are interconnected, there is a greater opportunity or affects the frequency in larger margins. So we have to have a dedicated controller which can able to control the frequency at a fixed margin. If you are unable to control the frequency at a fixed margin, the system, as you know, the generation is a star connected generator, transmission is delta, and the load distribution is again back to star. If you have a multiple frequency of not the rated value, you generate frequency of different values, and these frequencies can generate a lot of heats in the systems, and homopolar components are zero sequence components between the loads. So the reliability and the lifetime of the system can largely affected. For example, a simple solution I can say, if you have a good batteries, photovoltaic panels, when you're injecting the grid with a different frequency, the designed lifetime cannot be achieved with these electrical equipments. Another example is a simple example is the electrical clock, where if you are not having a constant frequency, you can't able to maintain the time intervals of the clock for periodic values. Then what is a base for load frequency control? The kinetic energy. The kinetic energy is given by 1 by 2 I omega square. So omega is the angular frequency, omega equal to 2 pi f. So your kinetic energy is directly proportional to the square of your frequency. If a small deviation in the frequency can have a large variation in your total kinetic energy. So in order to go for the analysis, we keep delta F is a small change in the frequency, a large change in the frequency sensed by your sensors which are available in the power system. Usually we keep voltage sensors and current sensors at which measures the AC voltage and AC currents. Then we calculate what is the frequency through the calculations by using phase lock loop systems or advanced equation methods. We calculate instantaneous frequency and we find the difference, and the controller tried to make this delta F to near to zero, so that you will get a 50 hertz in your complete power system, so that real power will be balanced between the input from the generator and towards the output on the load side. In order to go with the characteristics is very important. The governor characteristics of a single generator is shown here. The x-axis represents the load of the unit in megawatt or per unit, in per unit 0 to 1, and the y-axis represents the speed of the generator. So you can have a look at when the load is zero. It's a standard, if you had studied electrical machines in your bachelor's, it's a standard characteristics. So when the load is zero, there is no load on the generator, you get the rated speed. As the load increases, the rated speed of the machine will drop a bit. I say around 1.5 percentage maximum to a lower speed. So I can give an example. If the speed of your generator is 1500 RPM, when there is no load on the system, when you start loading the equipments, electrical equipments on your generator, as you increase near to the rated load, the speed drops, say around, it's not 1500, it can come up to 1420 or 1450. So that is a 50 RPM drop can occur. So this is a very generic characteristics with respect to your generator. So in order to calculate, again, we are going back to the basics. You know the value for the regulation. So speed regulation, here the textbooks give a new variable R. In many textbooks, the regulation is given like a yes or different variables. But here in your textbook, we used R as a speed regulation variable, which is given by N naught, which is a no load speed minus full load speed divided by full load speed. So this is a standard formula to calculate the speed regulation of your generator. Then how to calculate the regulation with respect to the frequency. So the frequency can vary between 2% to the 6% for any generating units, where the regulation of your frequency is the same as like the speed, no load frequency minus full load frequency divided by full load frequency. And obviously, in standard application, we go for 4% speed regulation of a unit with a rated frequency of 50 hertz. Then the frequency can drop up to 2 hertz. So for example, I have 50 hertz at rated conditions. As the full load increases, the frequency can go drop to maximum 2 hertz. That's why in our power system, we are unable to maintain 50 hertz. The generators from the generating units try to provide you 50 hertz frequency, synchronous generators. But the loads, we have variable loads, inductive, capacity, resistive loads, mostly inductive loads, and the loads are not constant and continuously regulating from peak to minimum or base load. That's why your frequency drops around 2 hertz. So it's a standard scales we used for frequency analysis. So, or I can say R is equal to minus delta F by delta PG, where your delta PG is the generation is increased by a factor of delta PG due to a static frequency drop of delta F. So this is a standard formula for calculating your frequency regulations with respect to the power generation, small change in the power generation with respect to the static frequency changes. Do you have any question on this slides? Then I'm going to look at the two different operating margin. That's very important for the synchronous generator as a speed govern settings. For example, first case, the y-axis varies for the speed and x-axis varies for the power, say around 0.25 per unit to 0.5 per unit. First characteristics is taken when there is no load. You can see it goes to the rated speed. As the load increases, the characteristic drops down as expected. And we are taking another margin which is around greater than 98 percentage. So we are looking at the second characteristic of your speed governing characteristic of a synchronous generator. When the load is minimum, the speed goes to the maximum. As the load increases, speed slightly drops. Now we are interested in looking at the characteristics on 0.25 per unit. It's like 25% of your load and 50% of your load. We are trying to draw the characteristics for the first condition of the operating margin at the rated condition. So you can see we are getting around 99% speed. When it is near to 50% of your load, the speed drops by 1%. That's why is a practical example. That's why your frequency also varies a maximum of 2%, which I already showed you in the last slide, and maximum it can go up to 4%. So an example where we get at rated condition 99% at 25%. So at 25%, there is a drop of 1% speed. At 50%, you get 98, 98% speed. So it's a 2% drop from the rated condition. This shows you a clear characteristics how the load plays an important role with respect to the change in frequency. That's why we are going for a constant frequency control in the perspective of power system. Please note this is just for a one generator. But in the complete power system, we have n number of generators. So every generators we want to operate at the same speed, same delivery of the voltage. That is the expectation of the power engineers. So in this case, why is the major goal for going for this characteristics is to keep the frequency constant. So the type of shifting the frequency or the speed characteristics parallel to itself is known as supplementary control. What is called supplementary control? Supplementary control is the process of shifting the speed or the frequency characteristics parallel to itself. It's called supplementary control. For example, you can have a look here. I have one type of speed which is around 99%. Parallelly at 50% load, I have 98%. So we want to control between these two margin, then it is called supplementary control. And level L, we mention a new term which is called speed control mechanism in in frequency control of the governor. So we introduce a variable called L, which controls the speed control mechanism. And R is the regulation of your frequency for proper coordination of the complete power systems, even during offline condition monitoring. Either in online monitoring or offline monitoring, we calculate what is R in order to maintain your frequency regulations. So usually what is the unit for R? Unit for R is hertz per megawatt. In practice, we also use hertz per unit. because we want all the megawatt to be represented in per unit scales. Any doubt about this slide with a single synchronous generator, how the speed governor characteristic is particularly set for frequency? Why we call the speed characteristic? Because speed is related to the frequency directly. 120 F by P. Any doubt about step by step we are moving towards the controller? Any questions? Okay. So now how to adjust the parallel operation of the characteristic of a single generator unit? You can have two units. Now we are taking an example. We have a governor characteristic of two different lines. For example, the first line is here. You can see on your right hand side. On the left hand side, you have the second line. So there are two lines feeding the systems. So this is an example how we are sharing of load by two units, which is operating in parallel with speed governor characteristic settings. So there is no load. You have the rated speed for both the lines, line 2 and line 1. As the load increases, of course, for line 1 and line 2, there is a drooping of your speed characteristics from the rated value to a minimum value. You can see on either both the sides. Now I want to control this power system for the rated frequency. Both should have the same frequency and both should have the total power delivered should be a summation of both the lines. Then the rated frequency of the both the system, let it be FR. And the system load required from the both the line is going to be P1 and P2, where P1 is the power from the line 1 and P2 is the power from the line 2. Now I'm going to look at the characteristics at two different power points, or say this is 0.25 per unit or zero 0.5 per unit. I can say this is a 25% of your load or 50% of your load. Similarly, on the line 2, 25% and 50%. I'm just picking up the line towards my speed plot characteristics. You can see at 25%, I just touch this margin. Of course, I put it here and extend the point P2. So when you're operating between P2 to P1, the total power, say P2 to P1, both the lines will have the same frequency. See? So this is the point I have to calculate for synchronizing the lines 1 and 2. Similarly, if I look at the point, for example, at P1, 50%, this is P1 dash. I'm extending the point from here to here. So I touch here, I extend on similar to the line 2, I got P2. So P1 dash plus P2 dash is the total power demand at 50% operating conditions. In general, I can say the frequency will drop down from margin 1 to margin 2 if the load is varying from 25% to 50%. The total power demand also changes with its operating range from P1 dash plus P2. So this is illustrated by a simple diagram on the speed governing characteristics when you have two lines, 1 and 2. Any doubts? So please note, this is the frequency and this axis is the power. And this is the variation of your power and frequency with respect to the first line. And this is the variation with respect to the second line. By virtue of its operation, already they are not having the same frequency. Please have a look. They don't have the same frequency. There is a small variation between both the lines. That's why we are very interested in looking at a frequency control of interconnected lines. So this is interconnected lines. So already the power system has a small deviation of the frequency. For example, the first case, the frequency is much higher. Second case of the line is little lower than the first one. Then how we are synchronizing the difference? It's simple. You apply at 25% and 50%. Consequently, look at the margin on the line 2 and add up the power. So for the first operating condition, it's P1 plus P2. For the second operating condition, P dash plus P1 dash plus P2 dash is the power delivered to the load. And if you look at the frequency for the first operating condition at 25%, you are very near to the rated speed. Both the lines are synchronized. For the second condition, the frequency drops to f dash. Any doubt? Then LFC control, we also called LFC, load frequency control, is also called as a power frequency control. So because we in the previous slide, I show you the characteristics where we look at the x-axis is the power, y-axis is the frequency. So LFC control, also known as generation control. Another name for LFC is generation control. Hereafter, I will say in a short form LFC. It's load frequency control or PF control in short form. This control is also called as generation control or ideal with the controlling the load of the generating unit for the system at normal frequency. So the aim of this control is to keep the normal frequency of the generating systems. As discussed, a slight variation in the frequency we will consider as a delta F, and we use command signals to make this delta F near to 0 so that you get the rated value of your frequency even if the generator is loaded to the full load conditions. For this, for example, a smaller variation in the frequency, this can be done manually. But for the large variation in the frequency, it cannot be done manually. It has to be done through the control system, advanced digital control systems for your LFC systems. So for small variation in the frequency, still now, many generating units uses manual controls. So it has been done by individually by the human efforts. But for the large variation, it has to be done by the digital processes to control the frequency by using PID controllers or PI controllers. But in LFC control, we doesn't require to consider the reactive power flow. We concentrate on only the frequency so that it control the active power, not on the reactive power. Then another one is we have a QV control, which is a reactive and voltage control. So this control usually done by sensing the parameters on the terminal voltage of the generators. So if you are working on a QV controller, you need to sense the parameter of your terminal voltage of the generator is sensed. And the sensed voltage will be converted into a DC signal by using sensors. We convert all these AC parameters into DC. So for example, I can give you a blind example. If you have a power on your generator is a 10 megawatt, the voltage which is generated from the generator, say around 10 kV. All these 10 kV voltage will be sensed, the sensors, and we convert these DCs into a DC signal. Maybe the amplitude vary between 0 to 3.3 volt. But if you are using a DSP, if you are using other digital processor, it can go up to 0 to 5 volt DC. So a large high voltage has been converted into DC, which can have a very low voltage signals between 0 to 5 volt or 0 to 3.3 volt, but based on the digital processor which is used in the application. For example, if you are using FPGA, it's going to be limit with 3.3 volt. DSP 3.3 volt. If you are going to use a D space, it can go up to 10 volt maximum, the DC. So that all the high power is converted into a low voltage DC where you get pure independent of frequency control. Then this signal will be compared with the DC reference voltages and you generate new control signals to control your voltage. For example, if the voltage error is delta VI, so I want to keep my load voltage also constant, but there is a small error that is sensed through delta VI, and this will be given to the input of your QV controller. The controller, what we give is the input. We will see with some examples later. So we give these errors to the controller for the QV controller, and the controller will generate an output signal which will control the reactive power of your generator by applying these voltages to your exciter. Because what is the significant uniqueness of your synchronous generator? Because by adjusting, maybe if you worked in real time with your synchronous generator, if you increase your excitation, decrease your excitation of DC excitation of your synchronous generator, you can able to control the synchronous generator as a synchronous condenser. It can serve as a capacitor. It can able to control unity power factor. It can work as a reactive power generator. That is a unique characteristic of your synchronous machine. So synchronous machine can work as a over-excited generator, under-excited generator, and excited generator. In excited generator, it will work as a synchronous generator. It deliver constant voltage. Of course, you can able to have a unity power factor, but you can also store like a capacitor. So when there is a reactive power, we can use synchronous generator parallelly in our power system. Obviously, it is being used large. We will see with some examples later, where your synchronous generator can work as a reactive power controller. They store all the reactive power generated from your power system and stored. And of course, stored energy can be delivered back to the grid. That is the advantage of using synchronous generator. For these control, what is the input? Your change in voltage, which is an error voltage. For example, I want 10 kV. It's an example, I'm saying a high power, but there is a 5%, 10% variation. Then I know the difference. That is the difference. I calculate, I give to the controller, and the controller will generate a new signal, which is a change in QCI. And this signal will generate a new voltage for your exciter in your synchronous machine. So you change the excitation, you control the voltage constant as well as compensating the reactive power from your synchronous generator. Any question about the slide?
Yes, I have a question. When you talk about the exciter, this is like an input to the synchronous generator, is that correct?
Yes, as you know, the basic characteristics of your synchronous generator, which is not available in your induction W-fed induction generator, is that by controlling the excitation angle, by controlling the DC applied to your synchronous machine, you can make your synchronous machine to work in three different modes or three different power factor: leading power factor, lagging power factor, or unity power factor. Or I say over excitation, under excitation, and excitation. So under excitation, it is like a normal generator. You generate constant voltage and unity power factor. Of course, you can work your generator as a reactive power compensator. For example, you have the capacitors. You put capacitors. The capacitors are static capacitor, but synchronous generator or dynamic capacitor, because you control the DC excitation voltage. You can increase the capacity of storing the reactive power generated from your grid into your synchronous machine. So that's an advantage of using a synchronous machine. That's why we are controlling the excitation applied to the machine. So for that, you have to please look the basics of a synchronous machine, where you can find the relationship between the power generated from the synchronous machine is given by a terminal called delta, which is called torque angle or power angle of your synchronous machine. So V1, V2 in sine delta divided by X is the standard formula for your synchronous machine. So you control delta. So delta is nothing but your excitation angle, which is also called as torque angle. Is okay?
Yeah, that's fine. Yeah, thank you.
Now we want to look at how in real time all these PF controls, so power frequency and QV control are really applied in the power system. Still now these controllers are used in practice. So if you look at here, you have a turbine, it can be a wind turbine or it can be a um, hydropower plant fluid turbine, or it can be a steam turbine. The concept is the same. So you're going to have only the change in the turbine. If it is going to be a hydropower plant, you're going to change this turbine based on a fluid turbine. If it is going to be a steam, then use a steam turbine for thermal power plants. If it is going to be a windmill, then you are going to replace this as by wind turbine. So this is the same because it's the prime mover for your generator. So on the generator, you have three terminals, which is the output voltage, AC voltage and AC current. Just now, one of the student asked me a question. You can see the DC excitation here. So one side we control the DC excitation, which is the DC power supply. Another side we have the output power. So the output power is a AC voltage, which is connected to the bus bar. You can have a look. It can be a single phase or three phase, depends on the applications. For this, what we are doing, so we have on the exciter side, we have an excitation controller. How the controller works, it based on the input from your QV controller. I already explained you in the previous slide what is a QV controller. So on based on the inputs of the QV controller, the input from the QV controller is the change in QCI, the change in the reactive power, which will be fed to your excitation control. The excitation control will generate a new DC voltage for the excitation of your generator. And what is this QV controller? In the QV controller, we have the parameter from your field winding, which is the excitation winding. How we get the input? We use a comparator to compare the voltage. You can see the generated voltage. The generated voltage is sensed to the through the sensors, and we find what is an absolute value. So your AC voltage is converted now into DC. Then we are comparing that actual value. So this is the actual voltage available from your bus bar or from your synchronous generator. We are comparing with the reference value. So what is my reference? For example, if it is I'm going to control in my lab, I give here a 440 volt or 400 volt. For a single phase, it's going to be 220 volts. So it's the reference I decide what I want the constant voltage to be generated. So the actual voltage from the generator is compared with the reference value. So VI minus absolute value of VI. So this difference is delta VI. So delta VI is nothing but VI minus the absolute value of your actual voltage. Then this difference error is given to your QV controller. In the QV controller, I find the value for what is the change in the reactive power compensation is required. That reactive power will be the input for your controllable excitation. So I have here again a power electronics converter. Here it is not shown. Consider as a controllable excitation. So here again I will have a DC to DC converter, or I will have a rectifier which converts AC to DC. Then I adjust the value of the that semiconductor devices by using these new error value. I generate a new voltage for the excitation. So I am controlling the excitation to get a constant voltage, one side of the control unit. And this is called AVR loop. What is AVR? Is called automatic voltage regulator loop. So this loop of controlling your excitation angle is called automatic voltage regulator loop. So this is the first part of your control system where I control the QV controller. The next part is PF controller. For the PF controller, I'm going to control only the inlet of the turbine, because this controls the speed of your generator. The speed is proportional to your frequency. So I always try to control the turbine inlet by using LFC control. Automatic load frequency control is applied only on the input side of your turbine, inlet of your turbine, or I say inlet of your turbine. It's not applicable on the generator side. On the generator side, I always use AVR control, which is excitation control. So what to do with this control? I have the error in the power. The error in the power is the input for my PF control. Then I need frequency. So what I do, I have the generator. From the generator, I sense the frequency sensor. Obviously, this is called a PLL, phase loop lock control. Usually the input will be voltage and current. From the voltage and current, I can able to calculate what is frequency, because when you have voltage and current, if you take a tan inverse of V by I, you get an angle of your voltage and current. It's of the power. It's the same for current and voltage. So you get the frequency. That frequency, I calculate what is the error with the actual value of 50 hertz. Then I feed to the controller. So I have two inputs, the error of the power, the error of the frequency. Then I give to PF controller. The purpose of the PF controller is to calculate what is the change in the power required for the control value frequency. So I calculate the power error in terms of frequency value, and I give to the control mechanism, which is a mechanical control unit of your valve. So I adjust this valve. When I adjust this the valve with the new values from the controller, I adjust the flow rate. It can be a hydropower plant or a steam power plant or a thermal power plant. Sorry, thermal power plant or steam power plant. Whatever, if I adjust the inlet wall, a mechanical wall is a mechanical parameter, I control the flow rate for hydropower plant. So when I control the flow rate, I control the frequency, which controls my delta PT, which is required for my generator. It's fine for you. So we have two type of control. One is AVR control. Another one is ALFC control. So this is for frequency control and this is for the voltage control. By adapting these systems, I can able to control a constant frequency and constant voltage from my synchronous generator. For this, as I said, we have a QV control. The QV control is called automatic voltage regulator control, and PF control is called automatic load frequency control. What is the objective? The objective is to control MVAR voltage, a constant reactive power mechanism of the voltage, and QV control, the mechanism is to control the stable output voltage. So QV controls the stable output voltage, MVR controls, of course, the reactive power compensation through maintaining the voltage at the maximum. Then on the ALFC control, we are controlling the voltage with the mechanism of delta. In the previous discussion, one of your candidate asked me a question, delta y we control, you see, you control delta by means of excitation so that you can able to get the constant output voltage at your synchronous generator when there is a small error of delta I. Of course, by controlling the excitation angle, you are controlling the reactive power of the systems of the large synchronous generators. So here, if there is a small change in the real power, so we calculate that is called error in the real power is delta P Ti. And what is the parameter delta PCI, which is nothing but the real power which is required from the generator for adjusting the wall in terms of frequency. And if there is any change in the frequency, we call it as a delta Fi, which is the error of the frequency. Any doubt about this control algorithm, which is adapted for controlling your frequency and voltage of your large power system? I have given you an example for one generator, the same applicable for n number of generators, and all these controllers will be synchronized. Any question? Then we are going to see, this is the most important. We have seen many electrical characteristics. And now we are going to look at in the point of control system, because control systems, we need blocks. How to represent mathematically all these large power systems in a simplest way. For that, I can show you here a linearized speed governor mechanism where delta XC of S. So all the control you already studied in your bachelor programs, of course, in masters with control systems. So all these needed to be represented in Laplace transformation. So Laplace transformation is the simplest way of controlling your complete system, because S is a free, it's a omega. So you are controlling directly your frequency, not the time. So that's a major application why we convert all the electrical parameter into Laplace transform. So this is an equation delta XC is equal of S is equal to delta PC, which is the um, change in the power, minus 1 by R. R is a regulation of your frequency into error of your frequency. This gives the difference between the error and the frequency deviation difference into KSG divided by 1 plus delta SG is the linearized model of your speed governing mechanism. How to represent that? Here is a block diagram. So my input to the system is delta PC of S, the change in the power. Change in power I already showed you in the previous slide. You can have a look, real power control signal. So real power control signal is given as an input. Again, I want to get the feedback. Look at the equation. So I got the frequency difference. Look at here how we are doing comparing here. So I have the frequency sensors. Then I get the error. Same we are doing here. So what I do, I get 1 by R. Look at the equation, 1 by R. Then I subtract. So I got this form. This was translated here. Then I want this block. I can use a block for representing KSG divided by 1 plus S into tau SG. And I get the output, which is delta XC of S. Here it's very important. What is the value of R? Your R is absolutely delta equivalent to K1 by K2. These K1 and K2 are the different speed constant coefficient gains, and they governs the speed regulation of your complete generator. Sometimes it can be kept constant, sometimes it varies, depends on the different setting values. And what is a KSG? KSG is nothing but K1, K3 divided by K4. And all these K1, K3, and K4 are the gain values of your complete generation unit systems. This is nothing but all these unit can be combined in delta SG, which is the time constant of your system, of your synchronous generator, delta SG, which is equivalent to 1 divided by K4, K5. Obviously, the value for delta SG practically will be less than or equal to 100 milliseconds. So when you know the value of delta SG, you can easily calculate what is your K4 and K5 by fixing one values, which is used in practice. So please note this delta SG is the time constant of your synchronous generator system. Now, what is the value of delta PC minus 1 by R delta FS? Is the net input to your speed governing system. So this is the input you are feeding to your system, and delta XE is the output of your speed governing system. So how to model mathematically the complete governor unit, speed governor unit is shown here. Any doubt? We have some examples. I will also show you with MATLAB how these modules are developed with a practical example. Of course, you can follow your textbook. In the textbook at the end, you have a lot of exercise. Around 20 exercise examples are shown for hydropower plant real applications with frequency control, voltage controls, etc. That can help you to exploit these concepts. Now we will take a break for 10 minutes, then we can join you. It's fine for you all?